Okay, you may start right now.
Good morning, everyone. Did you know that while you're sitting here, people have
Just
died
louder.
from
Louder.
coronary artery disease, which is counted to be one of the dangerous diseases, and the disease that kill many people all around the world. And scientists try to develop an equipment that try to help that from and prevent that from happening, and that thing is the stents. And stents have been developed for many years now, and it's our turn to develop one too. So this one is a comparison of the personalized variable vascular stents and arrow stents. This arrow stent is made by the Chinese people named Wen Wu. So we will measure the young product value and observe the physical feature through microscope. And we will test the stent in the blood simulation that we make from pump and pipe, and we will test it in 3 different conditions of blood, and which mimics the patient with diabetes, hypertension, and normal people with under control of the blood. And table of contents, we will have introduction, literature review, methodology and analysis on and simulation.
For the first part is introduction. Okay, before we go any further, let's take a look at what is biodegradable stent is. A biodegradable stent is a stent that made from biodegradable material. A material that can be decomposed by microorganisms, such as PLA, polylactic acid, and PLLA, polylactic acid. And the advantage of biodegradable stents are it can reduce the rate complications, such as thrombosis, and it has advantage of complete drug elution, and it also reduces the inflammatory response. And even though you can see that it has some of this advantage, but it's just some of it. And even some research study say that or discuss that this biodegradable stent can replace the permanent one. The next one is the negative Poisson ratio. This one is a technique that we use for designing our stent. And as you can see, we use this one, right? Negative Poisson ratio. This allows our stent to stretch simultaneously in every position. For example, when you stretch on the vertical part of the stent, the horizontal part of the stent also stretch too. And the next one is the printing technique. We print our stent by using 3D printer, and we use this technique to use deposition modeling. This technique is one of the 3D printing technique, but we decided to use this one. The literature review. So on the first paper, this one is talking about the study of biodegradable stent and design of negative Poisson ratio. So this one is our main reference. So in this paper, they are talking about the comparison on designing the negative Poisson ratio by using biodegradable stent and print it with the 3D printer. And in this result of this paper, they get the result that the diameter and the thickness of the stent can enhance the radial force of the polylactic acid stent. The second paper is this one. This one is talking about the technique that they use to print the 3D printer, the 3D stent. So they want to develop their own technique for printing stent. So they compare their own technique with the normal one, the standard stereo. the result is they technically can print the stent in just 26.5 minutes. We use this one as reference for decision for using which technique for printing stent is better. And the third one, the third paper is talking about the structure of the stent. So in this structure that they use is oxalic one. They compare the oxalic structure with the normal one, the self-expandable. And they compare like which one is better. So the result is the oxalic one can overcome the limitation of the conventional SE stents. And we use this one as again decision for which design of the stent that we should use. And the fourth one is also talking about the oxalic structure, but this one is talking about the application of the oxalic structure. This one just to know more about the oxalic structure, what it can do. So maybe we can apply it with our stent.
Okay, so in this paper, they're talking about the blood rheology. The blood is considered to be a non-Newtonian fluid, which means that it has a non-constant viscosity, and the blood has a shear thinning property, which is a pseudo-plastic fluid. So if you don't know the shear thinning plastic is, I want you guys to imagine about the ketchup bottle. The ketchup bottle, the tomato sauce is remain solid at the bottom of the bottle. But when you squeeze it, you apply the shear stress on it. It has a low viscosity and the tomato sauce squirt out. So shear thinning properties are actually if you apply more shear stress, the lower viscosity it is. And this paper also talking about the fossil law, which indicated a rise in the vascular resistance, show the company increase of water viscosity. In this, as shown in this equation, is a fossil law, and it showed that the fossil law indicated the length, the radius of the tube tube. So it depends on the geometry of the tube tube. In this paper, they're talking about the falling ball viscosity measurement. So let's talk about this method first. The falling ball method, when the observer throws the ball into the tube like this, the cylindrical group, the cylindrical tube, the ball will fall down with the terminal velocity. And in a traditional way, the observer use the stopwatch to measure the time at the start point and to the end point when the ball starts falling off to the end. And this is very hard to do this, to measure the time when it's hard, when the test liquid has a low viscosity. So it's going to be very, very fast. So the scholar Sarah H. Ali used the algorithm by using the smartphone camera to detect, to track the terminal velocity of the falling ball. So in this paper, here is talking about one of the earliest biodegradable stent that applied implanted into the real human in the year of 2000. Here is a picture of the stent of named Akaki Tamagi stent. It is a toy stent made out of PLA or polylactic acid, which is considered to be the biodegradable polymer. The design has a zigzag helical design, and the stents were implanted into the 15 patients in the year 2000. And The trial come up with a favorable result. There is no major clinical events related to the stent implantation occur in the 15 patients within 30 days. And there is no stent thrombosis occurs. Stent thrombosis is basically the blood clotting that is blocking the blood flow in the artery or vein, and there is no dead report in this trial.
And in this session, number 8, we will be talking about a comparison of balloon expandable stent implantation with balloon angioplasty in patients with coronary artery disease. So basically, this paper are talking about the stent with also balloon angioplasty in together, and to compare this one with the normal balloon angioplasty. So these two guys, the result of their experiment, they did the experiment with the patients in the hospital, and they tracked the luminal diameter. This line is stent group, and that dot line is the angioplasty group. You can see right here in the stent group, the luminal diameter is far more than the normal angioplasty one. So basically, you can conclude that when the stents combined with the balloon angioplasty, it can result very well in patient who has coronary artery disease. And this one is the follow-up state. It also going better than the angioplasty one, the stent one. But it's shrink a little bit, but you can count that it is still better. So this paper, I use it for those who want to use my research to have a future study. This can also be one of the way to do it. And number 9 is we use Archimedes principle. Basically, Archimedes principle has been done for a very long time. When once upon a time the king just decided to take a bath, and then he observed that the water out from the bath is equal to the volume of the water out from the bath is equal to the weight of himself. So he just made up the Archimedes principle from the mathematical logical sense, and he made up this one. This one is a hydrostatic pressure equal to density of the water times gravitational force times height. So this one, I use this formula in the paper in order to know the exact pressure in the fluid. And the last paper in literature review, we also use this one in our experiment. This one is the principle and application of Bernoulli equation. This one is basically the conservation of energy in the fluid. We'll talk about this later in the methodology part. Okay, so now we come to the methodology part. So this one is basically a simple, this first design is just a prototype. Just put a pump here and then just have all the pipe around there. This one is our simulation of the blood circulatory system. Okay, so now you may have question. When people are living, we live by a heart, and a heart have two different pressures. One is systolic pressure, and the other one is diastolic pressure. So how can we alternate this kind of pressure in the pipe? So I just decided to use the servo with a period of 1 second, because human heart beats every 1 second, right? So I have to use a period of 1 second. So when the water comes here, the part when the servo covers the hole, the pressure will be systolic pressure. And when the servo is out and not covering the hole, the pressure will be diastolic pressure. That's how I use, and this is the mechanism of our pipe and simulation. And we come to the same part. We use SolidWorks program in order to design this kind of stent, negative percentage O2. But we still don't know that if it's going to be this one or not, because math is too high. So we have to print it out first and stretch it, you know, to know that if it's negative consanguinity or not. And if it's not, you just have to do it again. But this will make it for logical sense. So that imagine you stretch it out, all the other side will be stretched too. So I just use my imagination to do it. But you can test it when we already in this state. And this is material that I use. We use pump, we use pipe, we use stents, we use beaker, we use 1.2 liter of 1 lakh fluid. We use 1.2 around liters of glucose, and more we can see of this one. And microscopes and gas, polylactic acid stream, which is very important because our stent is biodegradable stents, which is made up of PLA or polylactic acid. And we actually over time and need a tail. Okay, so this procedure is procedure A. I have to make the black fluid that have the same viscosity as the blood. But I still can't decide whether to use starch or aqueous glycerol. So I have to do the experiment first in order to know what I will use. So this one I have to take a break from it for a little bit. But let's imagine that I already made the black fluid that have the same viscosity and same density as blood. So in procedure B, I have to measure the viscosity of black fluid following the material part of the paper that Peerapat just said. Then they extract the boiling ball automatically depending on image processing algorithm. So it has a formula here. So let me explain to you guys the formula first. This one right here is a stroke law. Stroke law, and this FD right here is a drag force. Mu is a viscous friction. This is the thing that we want to find. We are going to find the viscosity of the fluid. And I said it is a falling ball with terminal ball with the liquid. And this is all the formula, and this one mu. D is the ball diameter, rho V is the ball density, rho L is the liquid density, and G is the gravity. So let's talk about this one. Okay, so I draw a free body diagram here right here. When the ball falling down, it falls in the constant velocity, right? So when it falls with constant velocity, it means that the acceleration is 0. When it is 0, then it has no force and it has no acceleration. So in that way, it is counted to be the equilibrium state. So when it is equilibrium state, in that part, all the force that applied to the ball are equal to net 0. So that is a key equation. So Fv is Gaussian force is equal to rho Vg, and that one is a 403 pi r cube is the density of the ball. Rho liquid is density of liquid, and G is the gravity, and plus 6 pi mu Rv is the drag force equal to mg. As you see here, mg is going down, drag force and volume force applied to the ball to go down, so everything should be net 0. So I use all the equation, and mu, that one right there, is a value we want to find, right? So we can find the viscosity of fluid after I use this actually whether it is starch or glycerol in order to do it, and I use this one to test and to know exactly what viscosity that I want to use in the simulation. Okay, now the procedure C. You know that I said that I have to alternate between systolic and diastolic pressure. So this one, the objective of this procedure is to alternate the blood pressure between systolic and diastolic. You know, when you go to the hospital, doctor or the nurse will come to check your pressure, right? So you have just the machine to squeeze your arm, and that one will give you two values. The upper value is systolic and the down value is diastolic. Actually, fun fact, systolic diastolic that you got is not the real pressure, it's a gauge pressure. So if you want the real pressure, you have to pass 30, 160, which is the pressure of the air, in order to make the low pressure possible. So now I want to find two values, which is 130 and 160 systolic and 90 and 100 diastolic millimeter mercury. So what I want to find systolic pressure first. In this one, this is pipe and the pump. And when I pump the water out, it will go down. It will be in this formula, and I will prove it later on the analysis part. But this part I will just use it first. L is an independent variable. We want to find how much L will give us the ratio of 130 and 160. So we are just adjust L in order to get this kind of value. And when we already adjust that, we'll get two values of L, which is L that made 130 systolic pressure and L that made 160 diastolic pressure. So just keep in mind we have two L now. Another one is diastolic pressure. This is quite special because you have a hole that makes water comes out. Imagine when you have a pipe and the water just comes out, it will reduce the pressure, right? So that is how I reduce pressure from 130 to 90. So this one is special because we don't use L as a independent variable anymore. We use X, which is the size of the hole. So I have to adjust the size of the hole until it get a value of 90 systolic pressure and 100 systolic pressure. Just substitute the formula and we get this one. So now we have two L values and two size of the hole value or two X. Okay, so this is just a prototype. We just put the servo on it and put the stent in at the location according to our X that we found in the previous calculation. And then put the stent in it and put the servo on it. This is like the design that I already designed. And we just put the pump down for 5 centimeters, just for your information. Okay. Procedure D is our last procedure. We have to create a but-for simulation and also the ability to observe how the stent changes under the different concentration of but-like fluid. That I mentioned earlier in the introduction part that we will mimic three patients. One is the diabetes, one is the hypertension, and one is the normal people. That normal people is controllable for the stent and but-like fluid. And for the stent and but-like fluid, 1,260 mg glucose is to mimic the patient with diabetes. And for the stent and but-like fluid, 160 systolic pressure and 100 diastolic pressure. This is to mimic the patient with hypertension disease. Okay, let's talk about this one first. I just pour the 200 ml of but-like fluid in a little beaker and make a hole and place the stent in it and connect the side to the pump and inside to the pump. Actually, these all text just move like this. Yeah. And this is just for the stent and but-like fluid. This is control variable. And for the diabetes patient, which I mean that you use 1,260 mg of glucose. I just do like the control variable one, but just input 1,260 mg of glucose in the but-like fluid to mimic the patient with diabetes, where there is a high glucose in blood flow. And the last one is the stent, which is in the condition of hypertension disease. So I just have to make the pressure more to be 160 and 100 millimeter mercury. So just reduce the cross-sectional area of the pipe by 20.077%. That way, the pressure from 130 systolic to be 160 and from 90 diastolic to be 100 systolic pressure, diastolic pressure.
Okay, so I'll talk about the analysis part. So he stated earlier about the blood flow simulation that has a pump and the blood moving fluid flow. So before I will analyze the simulation, we have to know about a little bit of the background knowledge first. The first equation is about the continuity equation. The A1 V1 equal to A2 V2. The A represents the area, the cross-section area, and the V represents the velocity. And the second equation is the Bernoulli principles. P1, P is just the pressure, and this term right here represents the kinetic energy, and right here represents the pressure in the presence of height. And the third equation is the Hagen-Fossil equation, which will be related to the blood flow. So our simulation have a pump right here, and we pump the blood, limiting fluid to the end of the pump like that, facing up, and we let the blood, the fluid, coming out of the end at the end of the tube, and find the maximum height H right here. So I indicated the 3 points right here, point 1, point 2, point 3. So the point 1 from the Bernoulli laws, I propose this term P1 plus 1/2 the kinetic energy term and rho T(H1). And equation number 2 is just like equation 1, but with a different height. The H2 represents the y is equal to 0, because I assume that because the simulation was placed into the floor, right? So there is no height. So I assume that the H2 is equal to 0. So it's a cancel out. And so, as from the Bernoulli law, we make the equation 1 equal to the equation 2 right here. So let's get back to the continuity equation. As you can see right here, the point 1 and point 2 have the same cross-section area. So the A1 and A2 will be equal, so it will cancel out each other right here. So we will get the V1 equal to V2. So if we substitute the V1 into as a V2 right here, these two terms basically are the same term, so it's cancel out, and so we will get the P2, which is the pressure at the point 2 right here. It's equal to the PA plus the rho H1. This is the H1. So you might be wondering why the P1s come into PA. PA represents the atmospheric pressure. So you will see right here the point 1 represents with the atmospheric pressure. So the P1 will be automatically turned to the PA, which is the atmospheric pressure. So to find the pressure at the point 3, we use the Hagen-Fossil law right here. So the delta P right here is the change of the pressure between 2 points. So we use point 3 and point 2. So we substitute like this, and we will simplify the equation. We get this equation. So the term P2, as we calculated for the previous slide, we will substitute them. We will get this equation right here. So the next following slide we're talking about is the preliminary result. So this is our picture of the initial design of our biodegradable stent. This is the stent unit cell. It represents the unit of the whole of the stent right here. So as Peerapat say earlier, we just use the imagination. to design our stent. So in the design, we use the equilateral triangle right here, which the angle will be 60 degrees and the right angle triangle right here. So if we combine the half part together, we get a heart shape like stent unit cell. And at the second step, we made a sheet, metal sheet, the sheet that presents in the SolidWorks program, and we made a geometric pattern of the unit cell, and we cut them off, and we roll it up, and we folded stem right here as our initial stem of design stem. So this is our reference. So if you want to discuss more about project, you can contact us right here. Okay, thank you for listening.
Okay, thank you very much. That's some question for you guys. Okay, why it needs to be a boson ratio? Oh, what is that? Can you explain again?
Boson ratio is to make our stent to make our stent be able to develop, stretch simultaneously.
What is the definition? Because you try to use that, you design by your own imagination in order to suit that thing. So what is the definition of that in the boson ratio?
It's a ratio of a structure design for the stent and many things that we do find. But we just apply this technique or design to our stent to make it be able to stretch. And it have many benefits, but I forget to say it.
So let's say like because you design that thing, that kind of triangle things, and you say that from your imagination, and you try to say that, to check that is to that ratio, right? How can you check whether it's a yes or it's a no?
We need to print it first.
Okay, and then what?
And then we stretch.
And then,
if the other part will stretch upward to that is the negative boson ratio.
Okay. So you have your own condition in order to make it.
Yes.
Okay. Next one. Why you choose to use the 3D printing?
3D printing. Many researchers or scholars use the 3D printing technique to design the stent because it is still initial stage of this design, because it's still not been used into the medical work. Yes, the medical work. It's just the initial design.
Okay, so you just try to make as a prototype.
Yes, as a prototype first.
From what you explained about the servo, the pump servo, you said that you're trying to make it as the 1 second. Yeah. Did you try it already? Because what I'm worried about, can it make 1 second per pump? Is that really? Can it make it like that?
Yeah, it can be possible.
Sure.
I'm sure. In the picture it has like this, right? And maybe adjust it to be like this, like this. It has many wings. Yeah.
Okay, so it can be 1 second per time.
Yes,
So if you said so, okay, so please, you tried already, not tried yet, right? But please be careful on that. Okay, what I suggest to you. Next one. That's kind of boring. Okay, the extent that you try to make it. Okay, like triangle thing, and you said it's because of your imagination things. Okay, but okay, let's say that because when you say about your imagination, okay, I suppose like you probably have your own reference things, okay, that you probably didn't recognize yet, okay. But I'd like you to make like at least based on something, okay, to make you feel that this is okay for you, okay, this is should be okay, it should be the best stent or even the appropriate stent. because you try to use your own way to create that, correct? Okay, but I like you to give some reason, okay, not because of your imagination, okay? Because when you say imagination, okay, it must be based on something, okay, that probably that might be reliable on. You understand? Okay, so this
Actually, we have some reference.
yeah.
That can
It's okay, but I know that it's okay shape already, okay, but when you said in the report or in the details, you just state your reason more, okay? It's not only imagination, because when you said when you show that picture, you probably show picture. That picture, because I used to see this kind of shape before, okay, I believe that this is kind of okay. Yeah, that state.
รูปสเต็ปของเรา
It's like
อ๋อ
Yeah. Because that shape, you see, yeah, I think it's okay because I'm seeing that before. Okay, so please just state the reason. Okay, why you use that kind of shape. Okay, you probably have like reference things. Okay, similar shape. Okay, probably. Okay, and you improve a little bit of that, for example. Okay. All right. Next one. You still deciding about starch or glycerol, correct?
Yes.
And you didn't decide yet.
Yes. I have to talk with the store and what the price and everything. I have to make it as one as possible.
Okay, so when you try to make the taste, correct? I don't know. Because this one you try to make it similar to blood.
Yes.
Okay.
This is the quantity and density.
Okay, so in the future you probably need to make for both, and you try to check whether which property is more similar to the blood. Is that what you trying to do?
I'm worried that if we starch, it will have some molecule that react with the stent and have some thing that all my control. But the glycerol is the safest way to do it, but I still don't know that the price of it and
we don't know yet. It is protocol.
I don't know, this is my idea, okay? I like you to try to make both first, okay, and try to check whether which one is more has the property, because if each one they must have some kind of each own property, and after that you probably check, okay, whether which one, okay, is probably similar to the close, I would say close to the real blood. Okay, that must be the way. Okay, for example, facial blah that you try to do the physics thing test, right? Okay, you probably can test that way. Well, this is one way. Okay, including your way, probably you can choose I would say the better one. Okay. The next one about how can you measure the pressure? You use the equation things, correct? Okay. And you said that is the point P1, P2, P3. So each P you use the different equation. Is that correct? Or the same equation? Because when you say about the P1, P2, P3, you try to measure, correct? Did you use the same equation? Or the different point, different equation?
We use many principle to apply to.
So I apply based on each point, correct? So you probably can show that slide.
Same main equation, but different value of variable.
Because when you present, I thought like the different one. For example, that one this one, for example, you got the point 1, point 2, point 3, correct?
Yes.
So each point you have the same equation.
Same equation but different value of each value.
For example, P1, how can you measure it?
To see by the leaf.
Verbally,
Yeah.
I get about verbally as well. You said that about you assumed that for the P2, okay, you got H2 equal to 0, right?
Yes.
P1 is as atmospheric pressure because it fills up the air. So in physical or physics, they just assume that it's using astronomic equation. So that's why I decided to he want to be PA.
Yeah. But in the next one, right? I'm not sure that you cancel because when you I think he said about the h equal to 0,
Oh,
and you cancel it.
yes.
Did you check with Ajahn? He said it's okay to apply h equal to 0.
It all comes from me having conversation with him.
Okay, so he says so it's okay, alright. So okay, so you try to use those equations to measure P, correct?
Yes.
Okay, fine. What I worry, okay, one condition that you try to mimic, the condition things to be exactly like that, I think it's previous slide, right? You got like condition of the situations that, and you try to mimic. Yeah, that one. Do you believe that you can mimic that situation exactly like that?
It depends. And I say that I haven't decided between glycerol and starch. If I use starch, I cannot use glucose anymore.
Yeah.
So I just cancel them out. This is two choice. I will just choose one of them.
Okay, got it. Okay, so because this was just worry, okay, that it might not be able to make it 100% perfect like that. Okay, so be careful on that. Okay. And also, okay, if in the future that you test it and probably it's not 100% exactly like that, that will affect to your research or not. So think about it. Okay. Sometimes it's not good as you expect. Okay. I think that should be all. Okay. All right. Thank you very much. Okay, very good.